My name is Rahul. I am working at TradeAt from last 7 years. And today we'll look at page attention. This is the future feature in vLLM. So this is the feature which made vLLM into the LLM into the vLLM. So today we'll start this session with the introduction to the LLMs, what the problems which we have in the LLMs, how the memory is managed in LLM. Then we'll jump to the vLLMs and then to the page attentions. Then we'll look what is the page attentions, how it works, what is need of page attention, then what are the benefits of page attentions, and what is the real world impact of these particular functions. Then we'll see the example, then how we can integrate this particular function into the systems and what are the future directions of this particular feature. So you might all be aware that LLMs is the model which can process your data and it will give you the answer. With the introduction of these large language models like GPT and PLMs, so it opens the vast fedora of, or you can say, the new world of applications like summarization tools, then your program helping tools, then you have some nice translation tools, and there are a lot of cloud companies which are trying to monetize this opportunity. So they are trying to develop this tool and then give it to the user and earn some money. But earning money is not easy with the LLMs because it requires a lot of memories. So the problem with LLM is it could not able to serve the model efficiently with whatever the GPU it has, because there are some issue with that. We'll see that. If you see the diagram here, so we have taken the example of NVIDIA A100 GPU, which is of 40 GB size. When the models get loaded, then it gives 26 GB of memory straightforward to that module. Then it will give almost 30% of memory to the KV cache, and we only left with 5% of memory to token activation and all the other stuffs. And because of this LLMs could not able to serve efficiently. It required a lot of GPU powers, and because of that we could not able to serve concurrent requests at the same time. If you see here, this is the graph of this is a graph where it will show how much batches it can serve at a particular time and how much memory it required. If you see this the first example, as the batch size gets increases, the utilization of GPU memory is also get increases, and you can see it can only this much of less than 10 batches it can serve at a time. But if you see another graph, the blue graph, it is for the vLLMs. So with the same GPU memory, we can access almost 35 to 38 requests at the same time with the same memory. So that is the issue with the LLM. So it could not able to utilize the GPU at its full capacity, and the US systems get inefficiently runs because there are so many requests it could not able to process. So this is how the memory is managed into the LLM. So if you LLM, so you can see there are three types of fragmentations, three major sources of fragmentation. One is internal fragmentation, the other is external, and there is some space which is kept for the future purpose as well. So you can see this is the request. So from here to here, so if you see, the user has only given the 7 tokens to the system, but the system assigned 2048 tokens, that 2048 bytes of memory to that particular request. So we are using only this much slots. This one slot is for the generated token, and then these 2 slots are reserved for the future purpose. I'm not sure when we can use that, when we get chance to use that. But this is one of the memory fragmentation happens with the LLMs. As our request is of only 7 tokens, it means these 2038 slots or bytes, which are never going to use. So system will just assign those. It will be empty throughout the operations. And these are the two. There are some. So we already. So when this process happens, at the time there are some blocks which was kept empty by the or token or slots kept empty by the systems. So we call this as external fragmentations. So this is the one issue, and because of that, LLMs sucks, or we could not able to use it properly at its capacity. So to overcome this issue, vLLM was introduced with some features called PagedAttention and the batching, which was improved the capacity of your GPUs more exponentially. This project is funded by or supported by UC Berkeley and LLM systems. The key features of this project is there are near zero latency. It uses almost all the memories or what are the GPUs we have, and we can easily deploy this process, this tool with Hugging Face or Open AI style API. So what is the memory attention? You might already aware about the swap space, which is used in Linux. So in the swap space, what we do, if there is any inactive pages, we just move it into the secondary memory and only keep the active pages into the kernel space. Okay. So like the same, this PagedAttention was inspired by the same concept. So here we use memory paging to efficiently serve the pages. So what is the need of the PagedAttention? So as I told you, the traditional LLMs which we have are memory hungry. So to reduce the cost of operations, to serve more requests at the same time, and to serve more requests at the same time and reduce the memory waste, we need PagedAttentions. So how PagedAttentions work? We can split it into several parts. Like the first is how the pages were demanded, then how the reuse page, we can reuse the pages, then how the key and value pairs are stored into the memory, and then how the duplication was handled by the PagedAttention. So on-demand paging means it will only allocate the pages if it is needed. If there is no need, then it won't allocate the pages to the request. It also breaks the KV cache into reusable memory blocks or pages. Then these pages are managed in the virtual address space, and so I will tell you how exactly it will happen in the next slides. So here we can see, I will show you how exactly the n array was created. So if you see this particular array, so this is the array which is created for each request. So as we are taking the example of CUDA platforms, which is used in the NVIDIA GPUs, so the default page size can be 16 tokens per request, or can be 32 tokens per request. So here we have taken the example of 16 tokens. Then the n array or the tensor can be written as this. The shape is equal to number of layers, then number of heads, and then page size and head dimension. This is created for each and every request. So here, as number of layers means how many transformer layers are there. So on the basis of that, we can say 12 or 48 or 128. It is depend on which model you are using. So here in the example, I have given the GPT-2 example, which use 12 transformers. That's why our number of layers is equal to 12. Number of head is number of attention to that particular transformer. So here in the example which we are given the 8, each layer has 8 heads. Page size. So page size, as I told you, page size can be different from 16 to 32. Here we have given the page size as 16. And head diameter, head underscore diam, which can be calculated from the formula that hidden underscore dim is equal to number of heads into head diameter. So from there we came with the value of 128 because we have hidden diameter is equal to 1024 and number of head is equal to 8. So here, if you see in the earlier example, as we see, there are 2048 blocks or tokens are assigned to the particular request. But here, if we have 2048 tokens, then the system will split those requests into 128 page, and each page will have the 16 token each. Then each token will have the page ID as well as the offset within the page. So here is the example. So if I have alphabet as a token like A, B, C, D, E, F, G, H, I, J, and I have given 4 tokens per page, then I will show the table. Okay. So here, so token 0, 1, 2, 3, 4, 5, these are the numbers of tokens which we have. If we have token 0, the page ID of that token is this page ID, okay, and the offset will be this, okay. These all records are kept in the indirectional table. So from the indirection table, you can see where exactly the token is, what is the location of that token. So in the page attention, the one feature is like dynamic allocation, memory allocation. So if we have one request which is having n number of tokens, then what system will do? If there is any requirement, then only system will assign the pages. There is a pool of pages, then from that pool it will just grab some pages and add the token over there. Yeah, if there is no space left in the last page, then it will just assign the new pages and it will append the whatever the key value pair we have to that next page. Page pool initialization is like when we have when the model starts, it will maintain the pool of some pages, like it is a bunch of pages kept there, and as we go forward as the request came, it will assign those pages to those requests. So during inference, the page allocation will also happen during the inference. So if we have, suppose if we have a 50 token request from the user, then what will system do? If we have the page size of 16 tokens per page, then it required 4 pages, and system will just allocate 4 pages from the free pool and assign them to that user's KV cache. And after doing that, it will just build that indirection table for that request. Token generation, it will allocate new pages as needed, as I told you. So if there is any any new request, and if we require more tokens, more pages for that, if there is some extra tokens, then it will grab new page from the pool and it will assign to that particular request. And when the serving of that request ends, then it will just scrap those pages and it will just move it back to the pool which we have for the pages. So this is how the pages are reused. So as I told you, if there is any request and which gets completed, then it will just move those pages to the pool. Unlike in the LLMs, what happens? So if there is any request, so it will save its future token as well as the past token as well. So it means if we have request of one request, then it will save 2048 bytes for the request, then 2048 for the future, and 2048 for the past. But unlike here, if the request get completed, then it will just move those pages to the pool again. Also, yeah. Uh, Yeah. So in our LLMs, as our memory frame is of 2048 bytes, but here, as all pages are same size, we do not have any holes into that uh, into the memory, and it helps to avoid the fragmentations. As this pools, as the pages are again added to the pool, and if there is new request, then we can again reuse those pages. That is one of the benefit of this page attention. So if you say, as compared to the LLMs, here we can use hundreds or thousands of requests at the same time, because we are using the pages dynamically. There is no fragmentation of memory because we use the page size are same, and that's why all the pages are used efficiently. It is also cost efficient because as compared to the LLMs, we are handling more requests, more users at the same time, and the time between your request and the response is also minimum as compared to the LLMs. So if you see the real world impact, so it is huge. It can help you with the translation and summarization, the real-time translation and summarization. You might see already some application into the market that they can translate your speech into the real time. So those applications are using the vLLMs. It also reduces the cost of your system by multiple of 3 or 10 or more than that. It also help you to process your legal documents. So I think legal documents are one of the most complicated documents, but with the help of LLM, you can process those documents as well. It helps you to reduce the latency as well. As you might see during the peak hours, then GPT will give you, it will take some time, but with the help of vLLM or the page attention, that time also get reduced. So if we take an example of a mid-size company, which is using the vLLMs for support, the chatbots for their support, customer support chatbots, then before this vLLMs, which can only take 4 sessions at a time, but with the help of vLLM and page attention, it can up to 12 to 16 sessions at a time. In the earlier technology, that is LLM, there is almost 60% of memory which is get waste, but with this vLLMs, less than 10% memory is waste. Means we are almost 50% of memory we are using efficiently. So latency per request is also reduced by half. So earlier it was almost 800 milliseconds, but it reduced to 400 milliseconds. And cost per 1 million inference is also reduced from $12 to $4.5. So it is popular in the startup companies because they want to reduce their cost. So most of the small case companies and startup companies are using LLMs and vLLMs for their operations. So we can integrate this particular tool with the LangChain, Llama Index, and Fast API. It also supports OpenAI clients, libraries, and tooling. It is also compatible with Docker containers, Dockers, Kubernetes, and scaling for scaling. There is also active community, and we have the active GitHub repo available. So as a future direction, they are planning to introduce multi-model and multi-tenant support. They are also planning to work with image and text data, and also efficiently share the GPU across multiple models or users. They are also planning to add hierarchical paging paging, uh, extend paging beyond token level to session level. As of now, we are only talking about these tokens, but they are planning to introduce the session level memory groups as well. CPU GPU hybrid KV cache, offload less used pages to CPU or NVMe with fast retrieval. Then model aware paging, adaptive page sizing based on model architect, and integration and distributed systems to make the page attention cluster aware. So these are the resources from where I just get the slides or the knowledge. So you can just go to this docs, this GitHub repo, and there are some logs from the other companies. So we at Red Hat, we are also using the Red Hat AI, which also use the vLLMs to host the models. Thank you. If you have any questions, please welcome.
So what's the impact on the actual inference time compared to without using it?
Yeah, so see, earlier you have 20, sorry. The question is what is the effect of this vLLMs on the inference time? How it can help the inference time to get reduced? That's right?
I was rather wondering whether the added complexity does not increase actually inference time. If I have, let's say, I have only the GPU for myself, I'm not batched or anything.
Yeah, so I will give you some. I will just give you an example. So suppose you have the LLM system. We are just considering the LLM system. So we have to do some civil work, and we decided that for that particular civil work, there will be requirement of 100 men. Okay. So if that 100 men work for the 8 hours, then they will finish that particular job in 10 days. Okay. That is the scenario. But what happened? Then we decided that from those 100 people, we will keep 60 people just for the reserve, and we will give some 20 people a particular work to just fill the water or just carry the bags, and the 30 people will only do the actual work. So this is happened with the LLM, and because of that, we could not able to finish that work in a particular time. Okay, but in the vLLM, what we are doing, we are just asking all the 100 people to do the work. And if there is someone who finished his job, then we'll ask him to do some other work. Like that, we are finishing that 100 days work or whatever the work we have into lesser time. So this is the core concept behind this vLLMs and LLMs. So in LLMs, we have 2048 bytes or the tokens we assign to the particular request, whether we have that much tokens or not, still we are assigning that particular bunch to that particular request. But in the LLMs, we are just splitting that into the smaller chunks and asking them to serve those requested as soon as they can. Yes?
Question about CPU, GPU, KV cache. This means that I can run a larger model which doesn't fit to GPU memory?
Yeah, yes. The question is like how we can, as we are sharing the cache in GPU and the CPU, then can we serve the larger models with the smaller smaller GPU and CPU? Yeah, the question answer is yes, we can. So as efficiently we are serving the memory, the pages, it will handle your request, the larger request than what is the capacity which we have. Yes.
Can you use the same concept of PagedAttention for not inference time but learning time?
The question is, can we use could you please repeat that question?
Do you use PagedAttention for learn time instead of inference time?
The question is, can we use the page attention for learning time instead of the inference time? So to be frank, I'm not sure with that, but yeah, if you give me your ID, then I will help you with that. Yeah. Someone from here? Yes, sir.
Yeah, I wanted to ask comparing to usual memory management on the CPU, right?
Yes. So the question is, so it is more likely, it is not like what we do in OS. So it is more likely sharing the memory in GPU and the CPU. That is correct?
The question was, it's more a technique or similar techniques having been used for dynamic memory management allocation for processes on the CPU till now, and not something that looks like virtual memory on CPU, where you usually need some support, some hardware support for it, something that creates exceptions or things like that. Well, it's not, because you know when it starts to be needed, and you know when it ends, and well, for my feeling, it's like dynamic memory.
We can say that it is like behaving like a dynamic memory, because we are dynamically operating or handling the pages, because we have the pool and then we assign those pages from that pool to the request, and then once the requests get completed, then we'll again send them back to the pool. Yeah, we can sort of like, we can say that it is behaving like the dynamic memory allocations.
Historically, dynamic memory allocators would also offer pools of different sizes. Are we doing that as well? Like, as I got it, if you don't need everything of one of these pages, this is more or less wasted. If you would have the possibility to combine, like, from a large block pool plus one at the end, a pool which has smaller blocks, then you could reduce the waste. Well, that's the idea behind these allocators for dynamic memory of the processes. Anything like that?
The question is really long, but I would like to, Miss I will answer your question after the session. But yeah, thank you.